Hello and welcome to the start of Methods of Theoretical Physics. This is the first topic of the methods part of the course, called Revision of Complex Numbers. As the name suggests, much of this material will probably be familiar to you, but it's still worth going through the video to make sure that we're all on the same page. So in this first video, we're going to cover some important groundwork that you'll use throughout the rest of the course. The intended learning outcomes for this part are: you should be able to use the Cartesian and polar representations of complex numbers in an Argand diagram. You should be able to use and manipulate Euler's formula. This is one of the most useful expressions that we'll use throughout the course, so you should be very comfortable with it. You should also make sure that you can use de Moivre's theorem for simplifying expressions involving trigonometric functions. You'll be able to use the problems provided to test your understanding of these concepts. And with that, let's begin.
We're going to begin by asking the question, why do we need complex numbers? So we already have a few different sets of numbers. That you'll be familiar with already. Okay, so we have the integers. We typically denote these by the letter Z with a double bar. And these are the whole numbers. So we run from minus infinity, minus 2, minus 1, 0, 1, 2, and off to plus infinity. We also have the rationals, also called the quotients. We denote these by the letter Q with a bar, and these are essentially the fractions. And we represent these as an ordered pair of integers. Let's say P and Q. And we understand this to mean the fraction P divided by Q. We also have the reals. And these are denoted by the letter R, again with a double bar. These are needed to solve equations such as x squared equals 2. We know that the positive solution, x is plus root 2, is irrational. In other words, you can't represent it as a fraction. In some ways, you can think of the reals as kind of a limit of the rationals on the real number line. So by increasing P and Q, you can get ever closer to a nice approximation of root 2, but you never get there perfectly. Okay, so we've got these three sets of numbers. What else do we need? Well, let's consider solving a quadratic equation. And the equation we're going to look at is z squared minus 4z plus 5 equals 0, where z is the unknown in this equation. So it's easy to plot the graph of this. I'm going to do that at the side over here. On the x-axis, we've got z, and on the y-axis, we're going to plot f of z, where f of z is this polynomial on the left-hand side. I'm going to change colour. And this is what this function looks like. It's a parabola. It has a minimum at z equals 2, and the minimum value of f of z is 1. Now, clearly, this plot does not intersect the z-axis. And what this means is that f of z equals 0 has no real solutions. Okay, so what do we do next? Well, for now, let's suppose that there are two solutions to this quadratic equation. Let's denote our solutions as Z1 and Z2. And for it to be a solution, it means that we can rewrite this quadratic equation as Z minus Z1 times Z minus Z2 equals 0. Now, how do we find Z1 and Z2? Well, let's plow ahead and use the quadratic formula anyway. So the quadratic formula, which we know from GCSE, gives us that the solutions to this equation are, looking up back at the equation above, minus b, which is 4, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 5. And then this is all divided by 2a, which in this case is 2. Now we can tidy this up a bit, tidy up factors of 2, and it turns out that this gives us 2 plus or minus the square root of minus 4 over 2. So these are our two solutions. Now this first bit is fine. This is a real number. This second bit is something new. Okay? It has the square root of a negative number. Now, rationals and reals can't describe the square root of a negative number. So, to describe the square root of a negative number, we invent a number I, which is defined as the square root of minus 1. And so I squared, I times itself, gives us minus 1. Now, looking at our roots, we need the square root of minus 4. So we can now write the square root of minus 4 is the square root of 4 times the square root of minus 1, which is 2i. Therefore, our roots are z1 is 2 plus I, and z2 is 2 minus I. And these are complex numbers. And it's easy to check that these are solutions by substituting in z1 and z2 into the expression at the top of the page. Right, so these roots are complex numbers of the form z equals x plus I, y, where x and y are real. So this notation here means that x and y are elements of the set of the real numbers. And we refer to x as the real part of z, and to y as the imaginary part of z. Now, in this form, it's quite straightforward to see that you can think of complex numbers as being ordered pairs of real numbers. So we can think of complex numbers as ordered pairs of real numbers. So in this case, it means that there's an association between the ordered pair xy and the complex number x plus iy. And importantly, the order matters. So the first slot in this pair describes the real part, the second slot describes the imaginary part. Now we denote this set of complex numbers by the letter C with a bar down the side, as we did earlier for the other sets of numbers. Now it's worth for a second thinking why we were still allowed to assume that there were two roots to our quadratic equation. And it turns out that this is all to do with something called the fundamental theorem of algebra. So I'm going to say it's worth noting that the existence of the set of complex numbers is necessary by the fundamental theorem of algebra. It's a very grand name. This fundamental theorem states, given a polynomial of degree n, so this means some function of, in this case, our variable z, which can be written as a constant plus a term in z plus a term in z squared, all the way up to the highest power, which is n. So given a polynomial of degree n, we then consider the equation f of z equals 0. This equation has n solutions. And those solutions are in the set of complex numbers. So in other words, the existence of complex numbers is a requirement for this statement to hold. We sometimes say that the complex numbers are algebraically complete. And what we saw above was an example of this. We had a quadratic, which is a polynomial of degree 2. And using the quadratic formula, we found that there are indeed two solutions. And in this case, the solutions were both complex numbers. Next, we're going to think about how we depict complex numbers. We said earlier that we can denote a complex number as an ordered pair of real numbers, x and y. And in fact, we can identify these components x and y as coordinates in an xy plot called an Argand diagram. So I can write this down as x and y can be thought of as coordinates. In something called an Argand diagram. An Argand diagram is a way of depicting the complex plane. So I'm going to draw some axes so we can think about what's going on. So our x-axis is the real part of our complex number. Our y-axis is the imaginary part. Now we can put down some complex number z given by x plus iy. And we can identify the real part of this as the coordinate x, and the imaginary part of this as the coordinate y. And from this we can now see that the set of complex numbers C is effectively a real two-dimensional vector space. That basically means that every point in the plane is described by two real numbers. And we sometimes write this as r cross r equals r squared. Now, this correspondence of complex numbers to vectors can be formalized a little bit. We can associate the real basis unit 1 with the x basis vector and the imaginary basis unit I with the y basis vector. And in this picture we can then write the complex number z equals x plus iy as a vector with x component x and y component y. This will remind you of Cartesian coordinates. There are a few other operations on complex numbers that look like vector operations. So for example, it's easy to verify that multiplication of z by a real number is equivalent to scalar multiplication of a vector. So as a simple example, if you take your complex number z and you multiply it by a real number a, you can expand that as a times x plus iy, which is ax plus iay. And equivalently, you can think of that as a xy is just ax, ay in Cartesian component form. Another similarity is the addition of complex numbers. So the addition of complex numbers behaves like vector addition. So let's take two complex numbers. One of them is z1 is x1 plus iy1, and z2 is x2 plus iy2. Now z1 plus z2, its real part is given by x1 plus x2, and its imaginary part is given by y1 plus y2. And pictorially, we basically have that some vector describing the complex number z1 added top to tail to the vector corresponding to the complex number z2 gives you the complex number z1 plus z2. So far we've been thinking about the Cartesian coordinate system for our two-dimensional space. But of course you know that two-dimensional space can also be parameterized using polar coordinates. So two-dimensional vectors can also be described in the polar representation. Let's again draw some axes to see what's going on. This is our real axis, our imaginary axis, and let's put in a complex number z. Now, as before, it has real part x, imaginary part y, but now we're going to instead describe it by r, which describes the length of the vector, and theta, measured anti-clockwise from the positive real axis, that describes the angle it makes with that axis. Now, by Pythagoras' theorem, this quantity r is given by the square root of x squared plus y squared, and as a result, we can see that r is positive, or greater than or equal to 0. This parameter theta is given by arctan of y over x. Now we're going to revisit this next point a little bit later, but for now I'm just going to note that we take theta to lie between 0 and 2 pi, where the 0 is inclusive and the 2 pi is exclusive. And we call these this range the principal values for angles in the complex plane. And as I mentioned, we're going to revisit this later in topic 4. Now, from this picture here, it's easy to read off that the real part of the complex number z, given by x, is r times cos theta, and the imaginary part y is given by r times sine theta. Putting these together, we can write our complex number z is x plus iy as r, lots of cos theta, plus I sine theta. We're going to quickly look at Euler's formula. Now, Euler's formula, often lauded as one of the most beautiful relationships in maths, states that e to the I theta, where e is 2.718 and theta is some real number describing the angle in the complex plane. This is given by cos of theta plus I times sine of theta. And this is so important that I'm going to put a red box around it. The proof of this relationship is probably easiest to see if you perform power series expansions of the left and right hand sides. So I'll just squeeze it in on the right hand side here briefly, that we know that we can write, and we'll look at this more later, we can write e to the I theta as 1 plus I theta, and then we get a minus sign because it's I squared, theta squared over 2 factorial, minus I lots of theta cubed over 3 factorial, plus theta to the 4 over 4 factorial, and so on. And we can partition this up as 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, etc. plus I times theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial, and so on. This first part is the series expansion of cos theta, and the part inside the brackets on the right hand side is the series expansion for sine of theta with an I in front of it. So we can see that e to the I theta is the same as cos theta plus I of sine theta. We can now apply this relationship to our expression above for z in terms of r and theta. So hence, we can write z equals r times e to the I theta. We call r, which is the absolute value of z, we call this the modulus, or the magnitude of the complex number z. And we call theta, this angle, we call this the argument of z. And together, this is sometimes referred to as the modulus argument form of the complex number z. As mentioned earlier, we choose theta to increase in the anti-clockwise direction. So the anti-clockwise direction from the positive real axis. And I'll draw a few examples of that to make it absolutely clear. So this is the real axis repeated a couple of times. And if we have a complex number, let's say, that points in this direction, the angle theta is plus pi over 2. If we have a complex number pointing in this direction, the angle is plus pi. And if we have it pointing in this direction, the angle is plus 3 pi by 2. Now it's easy to see that a full rotation of 2 pi brings you back to the same number you started at. So note that a full rotation of 2 pi brings you back to the start. In other words, you have z is r e to the I theta, and that's exactly the same as r e to the I theta, and then plus some multiple n of 2 pi, where n is an integer. Now, there are two more important observations. One will come from returning to Euler's formula. We have that e to the I theta is cos theta plus I sine of theta. Now, if we take both sides to the power of n, we have e to the I theta to the n is cos theta plus I sine of theta to the n. Alternatively, we can, when we take e to the I theta to the power of n, we can bring the n inside the bracket. So this is equivalent to e to the I n theta, and using Euler's formula as on the first line, we have cos of n theta plus I sine of n theta. Now equating the right hand side of these last two lines leaves us with cos of n theta plus I sine of n theta. I'll put brackets around here to make it absolutely clear that you're taking sine of n times the angle theta, is cos of theta plus I sine of theta to the n. Here as well. Now this relationship here is essentially linking trigonometric functions of multiples of an angle to powers of trigonometric functions of the angle without multiplication by n. And this relationship is called de Moivre's theorem. And I'm also going to give this a red box. De Moivre's theorem is very useful for writing down various compound angle formulae, and there are a couple of examples in the problem sheet accompanying this topic that will give you some practice. The second important observation is that multiplication of complex numbers is not the same as a vector product. And in fact, this is what makes complex numbers so special and so interesting. Consider z1 times z2, which in Cartesian representation is x1 plus I y1 times x2 plus I y2. Now we can multiply this out. This will give us x1 x2 plus I x1 y2 plus I y1 x2. And then multiplying the last two terms together, we'll get an I squared, which we know is minus 1. So we'll get minus y1 y2. So putting this as the real part first, and the imaginary part second. We get this quantity. It's a lot easier to see what's going on in the polar representation. And here we denote z1 as r1 eti theta 1, z2 as r2 eti theta 2. Now if we take z1 times z2, that's going to be r1 eti theta 1 times r2 eti theta 2. Now we can multiply the moduli together and bring them out the front. And these exponentials will have e to the I theta 1 times e to the I theta 2, which will result in theta 1 plus theta 2 in the exponent. And again, using Euler's formula, we can write this as r1 r2 times cos of theta 1 plus theta 2 plus I r1 r2 sine of theta 1 plus theta 2. And I'm not going to go through it, but it is possible to show that the Cartesian and polar representations of the product agree. And I'd encourage you to have a go yourself to check that. So in the polar representation, it's very easy to see what's going on. The rule for multiplying complex numbers is that we multiply. Let's have another go at that. We multiply the moduli and add the arguments. So we multiply the moduli, we add the arguments. And I'm going to draw two axes to give you a little example of this. One will be before multiplication, and the other will be after multiplication. And we have imaginary, real, imaginary, and real. Now we're going to be multiplying two complex numbers, z1 and z2 together. So I'm first going to put z1 in blue with an angle θ1, and another complex number z2 with angle θ2. And we multiply the moduli and we add the arguments. So the resulting complex number, z1 times z2, is going to be at a steeper angle, given by θ1 plus θ2. And its length is going to be r1, r2. This is z1, z2. So we can see that multiplication by a complex number can rotate and scale the vector you started with. As another example of this behavior, we can consider what happens to some general complex number z under repeated multiplication by I. So consider multiplying z by I repeatedly. Again, we've got real, imaginary, and we're going to start off with some complex number z over here. Now, if we multiply z by I, multiplication by I is going to mean the length doesn't change, because the modulus of I is 1, but you will execute a rotation by plus pi by 2. So in this picture, we're now going to be at right angles to what we started at. This is IZ, and the length is unchanged. So this is we've multiplied by I. We can do this again. We'll have another rotation by pi by 2. This is I squared times z, which is minus z. And so we've reflected across the x and y axes to get down to here. We can do it a third time to end up over here. This is going to be minus IZ. And if we do one last time, we'll get back to what we started at. And we get back to what we started at because multiplying by I 4 times recovers the z that we started with. So that's the end of part 1 of revision of complex numbers. To quickly summarise, we've looked at why we need complex numbers. In particular, we studied a quadratic equation that didn't have real solutions, but then by introducing complex numbers, we found that it did indeed have two solutions, as is required by the fundamental theorem of algebra. We looked at the Cartesian and polar representations of complex numbers on Argand diagrams. We also looked at Euler's formula and how to manipulate it to recover de Moivre's theorem, linking compound angle formulae with powers of trigonometric functions. And then to finish, we've been looking at multiplication of complex numbers, in particular in the polar representation. Thanks for listening, and next up is part 2 of revision of complex numbers.